Hello there, and welcome to the first episode in this series about the uses of space in the near and hopefully not too distant future. As this is the first episode, I feel I should give a brief explanation of what to expect of these videos and the series in general. This episode will be laid out like the others, though I think it's going to actually end up being one of the shortest of the episodes. First, I will talk about the subject of the episode. I'll explain its basic concepts, go on to give some real world examples from the past and up to a couple years in the future. Then, throughout the rest of the video, I'll develop the ideas, showing how the episode's particular branch of off world commerce could grow over the years and decades, what other industries could pop up around it, and how that would ultimately affect us down on Earth. For this episode, which is about manufacturing products in low Earth orbit, I'll go into how each product is usually made, like down here on Earth, and how that can be improved by the orbital environment, or why it can't be made as easily down here. Also, I'll try not to repeat too many points. In any case, it would probably be best to just start this. I don't want to lose too many of you before the episode even starts. So, building in space seems like a lot of trouble to go to when we've been making stuff pretty well on Earth for a while now. So, what are the advantages of manufacturing in low Earth orbit? Well, let's have a look at what the properties of low Earth orbit are. 1. Close to Earth. Obviously not as close as we're used to, but in the grand scheme of things it's still more convenient. 2. No gravity. 3. A natural vacuum. 4. No people around, which can be useful for some things. 5. Radiation, quite a bit of it. Not really something you want in most cases, but still. Also, not much to build stuff out of. Although there is stuff in space, it's obviously a lot less than we would find on Earth. Unless you want to go a bit further out. But that'll be a topic for another episode. For now, this industry is in a vacuum, so to speak. Only materials from Earth will be talked about in this episode, though many could and very hopefully would be sourced from elsewhere in reality. Mining the Moon and Mars and near-Earth asteroids. And we'll explore all of those topics in other episodes. So, what sort of things are people sending up there to be built? Raw materials? Some very niche process that just needs refinement? What's happening? Well, currently there are no companies manufacturing products in orbit at a commercial scale, though that does seem set to change in the near future. This area of off-world activity is still in the R&D phase. So, what's something people are researching or developing? Well, people are developing all sorts of things. Processors, fiber optic cables, more perfect crystals, even biological materials. Let's jump into our first soon-to-be extraterrestrial product, shall we? What are fiber optic cables? They're wires made out of glass that use a process called total internal refraction to transmit information. They connect the whole world from city scale all the way up to continent connecting ocean spanning networks. In 2019, a machine built by the Physical Optics Corporation was sent to the ISS for testing. This machine was designed to produce special fiber optic cables in the zero-G environment of the space station. So, why does this make better fiber optic cables? Let's look at how fiber optic cables are made. You get a glass tube, then you get another glass tube, then you fuse the tubes together with heat. Then you inject some special gas into the tube, then you heat up the tube, which in turn will heat up the gas, until that gas turns into the inner layer of the glass tube. Then you add more heat to the middle until it becomes malleable. This will collapse the inner bit and close off the tube, so it's now closed off at one end. You can then pull the tube apart, and from that it's a process of making it a lot thinner by heating it up and stretching it down. So it's quite a big tube at the moment, but it's going to get thinner and thinner and thinner as it goes down and gets stretched. Then you'll add a coating, and you can coil that around a drum for storage, and there you go. You've got some fiber optic cable. So on Earth, this stretching is done using a drawing tower, where gravity pulls the glass down under its own weight, stretching it as it becomes more malleable. During the stretching, heating, and cooling, crystals will form inside the cables. When working with glass, you do not want crystals forming, as glass is an amorphous solid, the opposite of a crystal. So these crystals are like impurities that fog up the glass in a way, and mean the maximum effective range and information transmitted by the cables is more limited than it would be without these imperfections. In space, it's believed they can do the stretching, heating, and cooling in a much more controlled fashion, so these crystals do not occur as often. It has been shown both in the before mentioned example and in an experiment done on a free-falling plane that these zero-G fiber optic cables perform better than their ground-born competitors. POC claims 10 times better, so this is seemingly no trivial upgrade. And with the high cost of fiber optics already paired with their low mass and very easy storage, we have a good candidate for an off-world commercial product. So since this product seems to be the closest to being produced in L.E.O, let's imagine how they could move the operation from an experiment box on the ISS to a full-blown industrial operation in space. I would imagine the first attempt at a larger scale endeavor would be a couple of single launch capsules meant to stay in L.E.O for the duration of the operation, producing the fiber optic cables, and then coming back down to Earth for a full examination of the product created and the machinery. Let's see how this could play out.
Harmony Space here with a world-first venture into space manufacturing. In partnership with Made for Space and SNC Space Systems, we will be making the world's first industrial facility off-world, constructing fiber optic cables 10 times more efficient than those currently in use. By this age of increased connectivity, humanity needs innovation to keep the flow of information as fast and reliable as possible. Zero-G Z-Plan is the answer. Our first steps have already been accomplished with successful tests on the International Space Station, and now we are scaling up production. 2 separate spacecrafts will be sent for this mission. 1 SNC Dreamrunner spaceplane and 1 Harmony S tin can. The Dreamrunner will take its payload to the International Space Station for 6 months of testing, during which time the astronauts will make adjustments for the full-scale machines that will be used to make our cable in the future missions. The tin can will be filled with multiple machines, making our first generation of cables. Once it has exhausted all of its materials, it will deorbit and come back down to Earth so that we can see how the cables and the machines deal with re-entry. After the Dreamrunner's 6-month mission, it will also deorbit and see how its cables and machines react to the much softer re-entry of the Dreamrunner. Once our scientists on the ground have perfected their manufacturing process and secured substantial orders for our superior fiber optics, we will move on to the next stage. So what are you waiting for? Whether it's advanced radar, military or surgical lasers, hyperspeed communication, or any of the countless applications of Zero-G Z-Plan, you will benefit from this new revolution in connectivity. Invest in space.
In space, mass is everything, and for an orbiting factory, getting the most profit out of the smallest amount of mass is everything. This brings us to our next product, human organs. Cardiovascular diseases are the top cause of death in almost all nations with a space program, and it's in the top 3 for pretty much every other country in the world. So far, transplants are the best treatment, so demand for human hearts is high, and depending on where you live and who you ask, a possibly compatible heart averages anywhere from 50,000 to $1 million US. Now, for something that only weighs about 300 grams, that's pretty good. But not only do 3D printed hearts not require the timely and tidy death of an organ donor,
They are also in very much higher quality. They haven't gone through the rough and tumble of a human life, and they will be made using your DNA, making them less likely to be rejected. Well, that sounds amazing, 3D printed organs. But why in space? So, as anyone who has dissected hearts for school or seen one at the butcher's will tell you, hearts are not particularly rigid like any normal printer filament. A 3D printed heart is clearly just going to fall apart during printing. I don't even want to know what abomination would come out of a human organ print failure. That being said, this technique has been used to create cardiac patches and miniature hearts about the size of a grape. But if we want a reliable production of full-scale adult hearts, we need to get rid of the constant drag of gravity. One method for doing this is to print the hearts in space and then bring them down to Earth for distribution. With the success of our Z-band cables, Harmony Space Agency is soon to become the first company to host a permanent manufacturing facility in space. The Revolution is a station made to produce Z-band fiber optic cables and transplant organs, comprised of 4 modules, a habitation module for the 4 technicians to do maintenance on the production line and to do research on better ways of producing the materials, a power and propulsion module equipped with solar arrays, a docking module for the spacecrafts and for EVA operations, and the production module made up of a central inflatable structure with 6 smaller inflatable protruding areas for better heat dissipation. This compartmentalized design provides superior protection for each individual machine, ensuring a malfunction in one area will not affect the other crucial production lines. To aid in the research, a Dream Runner will always be docked. Also, a tin can will always be docked, with raw materials being sent up and product being sent down every 2 months. The Dream Runners and station crew will be on 4-month missions to minimize adverse effects from zero-G, while allowing them to run worthwhile tests with a useful turnaround time. Each tin can returned to Earth, as well as providing zero-G Z-band cables for global usage, will carry hundreds of life-saving human organs perfectly tailored for the intended patient, with the minimal chance of rejection. Soon we will all see how space industry can change the world, but this is only the beginning. Invest in space. So where could this go? With a station no bigger than the ISS, multiple industries can be turned on their head. With the new space race bringing launch costs to a new low year after year, very soon we will not be limited to a space station like the Revolution or the ISS. We can actually build structures far too big to be stuffed into a fairing, even with inflatables and the most inventive folding techniques. But what we've been doing so far isn't really building any more than attaching a trailer to a tractor is building. How do you build in space? Well, we get all the materials there, and then the best idea will probably be to weld everything together. Specifically in the vacuum of space, welding can be a little different, in that you can actually do it without much heat. It turns out if you just touch 2 pieces of the same metal together, they can connect. It's called cold welding. The reason this doesn't happen with everything on Earth is the air, which with metal causes an oxide layer to build up on the outside almost instantly, meaning the 2 pieces of metal never actually touch and we need to use the normal methods. But if you take the metal into a vacuum and cut the end to remove the oxide layer, you can just stick them together. This is great news for off-world construction. We're here, folks, the start of a new era. The space age is upon us, and this is the next great leap. Humanity's first full-fledged factory district in space, Iron Bridge. Sent up in pieces, the structure of this imposing construct will be assembled by a growing team of astromechs sent up with each new shipment. Controlled by nearby Dream Runners, these robots are outfitted with everything needed to grab, move, weld, wire, and maintain. The first order of business will be to weld together the hundreds of metal struts to form the frame of the station. Then they will attach and construct appendages for the solar panels, radiators, factory modules, reaction wheels, and robot arms. After a bit more bulking out, the first factory module will arrive. Some assembly required, but our fleet of astromechs will make quick work of that. After it's ready, the robot arm will put it into position. After a quick testing period, the first tin can filled with raw materials and components will arrive and dock with the factory module so it can do its work, turning them into valuable space-age products. Once completed, the tin can will depart to bring the riches of the world above back to Earth. The Iron Bridge's factory modules have a mini-modular design to better accommodate a company's preferred scale of operation. The structure can be fitted with dozens of modules, and depending on how the space market develops, Iron Bridge can construct modules and space stations itself to excel in any role. Contact our design teams to book your spot. Invest in space. Well, here we are, a factory in space. As demand for off-world products grows and research continues, new products will be added to the orbital manufacturing complexes. Let's have a look at some more as the Iron Bridge expands. Microencapsulation, the process of surrounding tiny amounts of material in a coating for various reasons, making a biodegradable balloon filled with a substance. This is used for all sorts of purposes, from food flavoring to the latest anti-tumor drugs. You'll forgive me for focusing on the latter. The delivery of the drugs is simple enough. You inject the fluid containing the microcapsules that each contain the appropriate mix of anti-tumor drugs into the cancer site. The bubbles pop, and the drugs do their work. For this process to work properly, you want the inner fluid to be as spherical as possible. On Earth, microencapsulation is hindered because of gravity again. After tests done on the ISS on microencapsulation of cancer drugs for deep tissue cancers, researchers were able to discover how to replicate the drugs on Earth. But with the reduced costs of spaceflight, the production of these drugs might go back to their roots in space. Crystals are objects made of a repeating pattern of atoms called a unit cell. But crystals are not filled with perfect replications of this pattern. There are defects. Vacancy or Scotty defects are where ions are missing. An interstitial defect is where an extra ion is present where it should not be, and a Frankel pair is when an ion from a crystal is displaced to somewhere it shouldn't be. These defects affect the properties of the crystal, which can negatively affect their usefulness. An example product would be protein crystals used in many pharmaceuticals. During the formation of crystals on Earth, as the crystal grows, its buoyancy will diverge from the solution's buoyancy. This will cause it to move in the solution, which in turn causes a convection current around the fluid. This introduces defects, as the perfect growing conditions are not maintained perfectly evenly around the crystal. In space, buoyancy of the crystal will not create convection. Therefore, you can create more perfect crystals. Though these perfect conditions have since actually been replicated on Earth with the use of magnetic fields, in the case of protein crystals, it greatly reduces their growth rate when compared to natural microgravity. As we just said, gravity causes uneven mixtures of fluids. In alloys, the different densities of metals can cause uneven distributions. In 0G, density is not an issue. The alloys can be made completely evenly. If you remember back with Z-blank cables, the advantage of microgravity for them was that crystallization was much harder for that substance. This is true in this case as well, allowing for the formation of metallic glass. Glass meaning a solid with an amorphous internal structure. You want this because some metallic glasses are much less brittle than conventional metals. Some of these products do not need to return to Earth. A compound called gallium arsenide results in a lot of bad byproducts like arsenic, but can be used to make much better solar panels, converting about 40 to 50% of the light that hits it into energy, versus 15-20% for the panels here on Earth. But much like our products in 0G, no atmosphere environment allows for precise atom-thin layers of material to be made into semiconductors that can get these solar panels up to 60% efficiency, according to the University of Houston, who created the spaceborne semiconductors. Effective solar power is valuable in space as well as on Earth. As the off-planet manufacturing market expands, no doubt we will find many more products that can be made better in LEO, and the increased production capacity in space will help in making orbital infrastructure more essential, which will be needed for many of the other uses of outer space we'll be looking at in the future. Until then, I thank you for watching, and hope you will also watch the next episode, Space Tourism. See you then.